You know, the world all around us is just constantly moving. But what if I told you there's a kind of hidden language, a secret set of rules that controls everything, from a simple falling apple to a car speeding down the highway? Well, today we're going to pull back the curtain and uncover those rules. Just think about that for a second. What if you had the power to know exactly where a thrown ball is going to land, or how a fender bender is going to play out before it even happens? I know, it sounds like some kind of superpower, right? But it's not magic. It's just physics, and we're about to learn its secrets. Okay, first things first. Before we can even get to the why things move, we've got to have a really precise way to describe how they move. This is where kinematics comes in. Think of it as the basic vocabulary of motion. So right away, we hit a super important distinction. Let's say you walk around a whole city block and end up right back where you started. The distance you walked might be, say, 1 mile, but your displacement, which is just the straight line from your start point to your end point, is 0. You're back where you began. See the difference? Distance is just how much ground you covered. Displacement cares about where you ended up. And it's pretty much the same idea when we talk about speed and velocity. Your car speedometer tells you your speed, how fast you're going. But velocity is speed with a direction. Think about it. Hearing a storm is moving at 60 miles per hour is one thing. But hearing it's moving at 60 miles per hour north, well, now that's information you can actually use. That little piece of directional info is what makes velocity such a powerful tool in physics. And this right here is where things get really cool. This is where the real predictive power of physics kicks in. If an object is accelerating constantly, meaning it's speeding up or slowing down at a nice steady rate, these two little equations are like a crystal ball. You can plug in the numbers and they will tell you exactly how fast that object will be going and exactly where it will be at any point in the future. And speaking of constant acceleration, here's one of the most famous numbers in all of physics: 9.8 meters per second squared. That is the acceleration that any object experiences when it's falling freely near the Earth's surface. If we ignore air resistance for a moment, it doesn't matter if it's an apple, a feather, or a bowling ball. They all speed up at this exact same rate. It's like Earth's own gravitational signature. All right, so we've got the language to describe motion down. But that leads to the really big question, right? Why do things move in the first place? To answer that, we have to go from just describing to actually explaining. And that means we're diving into the world of forces, mass, and what we call dynamics. And this is the master key to the whole thing. Newton's second law. Force equals mass times acceleration. F equals ma. It's so simple, so elegant, but it's the fundamental connection between a push or a pull, that's a force, and how an object's motion changes as a result. This little equation is the engine that drives all of dynamics. This chart breaks it down perfectly. Just picture yourself pushing a shopping cart, okay? Now imagine you fill it up, doubling its mass. If you push with the exact same force as before, what happens? It accelerates at half the rate, right? It's harder to get going. But what if you keep the cart empty and you double the force of your push? Yep, you get double the acceleration. It just makes perfect intuitive sense. Now this brings up something that trips a lot of people up: the difference between mass and weight. Your mass is basically how much stuff you're made of. It's a fundamental property of you, and it never, ever changes, no matter where you are in the universe. Your weight, on the other hand, is just the force of gravity pulling on all that stuff. So on the moon, where gravity is much weaker, your mass is exactly the same, but you'd weigh a whole lot less. So we can describe motion. We know what causes it. Now let's get to the really exciting part. What happens when things that are moving, well, run into each other? Welcome to the science of impact. We're about to talk about momentum, impulse, and collisions. Momentum is one of those incredibly powerful ideas in physics. It basically combines an object's mass and its velocity into a single concept. You can think of it as its quantity of motion. For example, a heavy bowling ball and a light baseball could be moving at the same speed, but that bowling ball has way more momentum, and that's why it's so much harder to stop. And here is where physics literally saves lives. It's all about something called impulse. The big idea is that the force you feel in a collision is all about how quickly you stop. So if you want to reduce that nasty force, you just have to make the collision take more time. Think about it. Car airbags, crumple zones, even just bending your knees when you jump and land, they all do the same thing. They increase the time of impact to decrease the force on you. It's brilliant. So when things do smash into each other, it usually happens in one of two main ways. You've got your bounce collisions, which we call elastic. This is like a perfect game of pool, where the balls click off each other and no energy is really lost. But in the real world, most collisions are inelastic. They're the stick kind. Think of a car crash. The cars deform, they might stick together, and a bunch of that energy gets lost as heat and sound. Phew, okay. We have covered a lot of ground here, right? We've gone from just describing motion to figuring out why it happens, and then to analyzing what happens when things collide. So let's put all the pieces together. It really all comes down to these three building blocks. We've got kinematics, which is the language we use to describe motion. Then we have dynamics, with F equals ma at its heart, which gives us the reason why things move. And finally, we have momentum, which is the perfect tool to analyze the impact when things interact. Describe, explain, analyze. That's the whole picture. And look, if there's one thing I want you to take away from all this, it's this. These ideas aren't just abstract formulas you memorize for a test. They are the actual rules running the universe. They govern every single interaction you see, every day, from throwing a ball to driving your car. So I'll leave you with a question to think about. The next time you're watching a game, or you see a car slam on its brakes, or you just toss a set of keys to a friend, what are you going to see? Now that you know the hidden rules, how is your view of this world in motion going to change?